Okay. Sorry, my lighting's throwing a fit. So now, today we're going to talk about the third central moment. Last time we had squared because we wanted to capture deviation. So the motivation for this, if you couldn't guess it already, the third central moment is going to take our centering formula. We're going to cube it. And why we do this is we actually want to now, so when we had squared it, we wanted to show deviation. So we wanted to eliminate negative values. This time we want to preserve negative values. But the cool thing about cubing is that it will inflame magnitudes, meaning that it likely does not ever center perfectly on 0. Usually you're going to have a right tail or a left tail distribution. If this ends up being positive, that's indicating that we're going to end up with a right skewed distribution. If it's negative, it's indicating the opposite. So, working our example, we do these calculations first. So I'm really going to shorthand this. Negative 1.7 cubed multiplied by 0.2 plus, for this example, this is what we're using. If you're confused, you have to watch the other videos on my expectations operators and central moments leading up to the third. There's a reason why it's called the third. Don't start with it. Negative 0.7 cubed multiplied by 0.5 plus, and we have our 2.3 cubed now multiplied by 0.3. Probabilities of our centering itself cubed. This will end up equaling negative 0.9826 plus, minus, so we're going to get a negative value for this one too, 0.1715 plus 3.6501. That's going to give us, and these are approximate figures, so I should say this isn't equal to, this is approximately equal to 2.496. Now, if we want to talk about the skewness, there's actually a formula for that, so this is incomplete. This gives us the third central moment, which leads into the idea of skewness, but it is not skewness in its entirety. So the formula for skewness is this. So we're taking our third central moment, but we are dividing it by sigma to the third power. Sigma, in this instance, means standard deviation. Standard deviation is the square root of variance, and last time we had solved for the variance. So I'm going to give you that identity in the expectation operator form. So it's the square root of the expectation of x minus the expectation of x squared, and again, all under the square root here. So when we take this to the third, it's basically like taking our second central moment and raising it to the 3/2 power. Because if I take this to the third, we raise this to the third, but there is a square root here. So that's what's going on there, and that's how we're going to mess with this. So we end up with, actually recall from last time, I'm going to just kind of shortcut this for us. So last time we had already calculated what this value was. Then we take the square root, raise it to the third power. That's the same thing as taking 2.41, which again is our variance, or excuse me, yeah, that is our variance, and raising it to the 3/2 power. That's going to end up yielding us 3.6 0.74. So we've calculated the numerator here. That's this. Then we've calculated the denominator down here, recalling from last time that we know what the variance is. And then we just raise it to the 3/2 power because we're talking about standard deviation cubed. So this becomes 2.496 over all of this. This is the skewness divided by 3.74. So we can tell that this is positively skewed. It's rightward in its skew, so we have a right tail, and that should make sense. 5 is a significantly larger value, and there's a decent amount of 5s, but it's a significantly larger value than 1 or 2. So our distribution would look not too skewed, but it would have a little rightward skewing. You can tell this too. Basically, normal distributions will have a skewness of 0. So a perfect normal distribution will be 0. If we're slightly above, if we're below 1 but we're above 0, then yeah, you're going to have some slight skewing. But once you start getting up into higher numerical values over 1, 2, 3, then you definitely have some high rightward skewing. Or if you attach a negative to that, it becomes much more negatively, or excuse me, leftwardly skewed. So hopefully you found this useful. Next time, I bet you could guess it, we're going to talk about the fourth central moment. I'll see you then.